Online Physical Chemistry Lab for the fall 2023 has students doing Thermochemistry Laboratory as project number 2. And information about this can be found on a public website at biopchem.education. And let's head over to that website and go to the project information, scroll down to project number 2, and here we provide an outline. We provide a laboratory handout. I'm not going to open that here, but it's a PDF where students can go through the details of what will be performed in this online laboratory. And we provide links here for convenience. The lab consists of a computational component, primarily using molcalc.cloud, an online resource we've developed for computational thermochemistry. For more advanced or alternative computational resources, you can click here, and we provide links to both the ASU supercomputer and ChemCompute for more advanced thermochemical calculations. The remote experimental component will be done through a simulated experiment where we've developed a simulated of a classic bomb calorimeter for measuring the heat of combustion of materials and being able to calculate thermochemical properties from that. There's a remote differential scanning calorimeter, but for the fall 2023, this is an optional component that, for the most part, students will focus on the simulated experiment for the fall 2023. And then putting both the computational and simulated experiments together, doing data analysis, error analysis, and we provide a report template for students to be able to download here. So I've summarized an overview of this in a Google Sheet, and let's kind of go through this step by step to see the various components and the workflow that students will generally take to complete this project for ASU Online Chem 343. So we start by wanting to read the handout and do our own research as far as getting background and literature information about the topics we're covering. So things like basics of bomb calorimetry, the basics of computational thermochemistry for looking at heats of combustion, heats of formation, etc. And I recommend using Google Scholar or as an ASU student, Scopus for doing research and finding material to look at these topics and get background information from several different perspectives. And then as we do this, you can download from biopchem.education the report template and start crafting your introductory or background material and citations as you kind of get through this first component. So as an example, if we go to Scopus, log in as an ASU student, we can search for something like bomb calorimetry in physical chemistry or of various materials, etc., and see, various papers on the subject. When we find something of potential interest, like for example, using calculations to calculate the enthalpy of combustion in physical chemistry lab, this JChemEd article, we can view this article and start getting some background information. If we find this useful in helping us understand the background material and complete the tasks for our own project, then we might want to use this in our introduction, and so we can choose that article as well as any others, and come up here to export, and we can export that to various formats so that we can cite it directly into our report. We can also download that article. So we might also be interested in this, how you find the enthalpy of plastics. So again, we can click on this, and this is the same type of bomb calorimeter we're using or simulating. And it goes through, if you were to run plastic-like materials, some of the information, etc. So we can get a feel for some of this, and now we can immediately export those, open a template, say something like, the Google Docs I provide, and start summarizing some of that, referencing those citations, summarizing some of the background information in our report so that we're really working on our report step by step as we go through this project and not just saving it for the end. So now coming back to this, that gets us past the first part, and we've already started, making some headway on a report. We feel like we have a good background and have looked through various literature sources. The handout will start getting a sense that we want to, that bomb calorimetry usually use things like benzoic acid, naphthalene, azolene as standard materials, benzoic acid as it's to do the calibration of the bomb calorimeter constant, and that in this specific lab we're wanting to look at the difference between fatty acids and carbohydrates or sugars. And so we can start adding that to our background, that we understand some of the material, put that into our intro, and now move on to doing some computational analysis on these materials. So heading over to molecalc.cloud, for example, one of the first things from the background material we'd see is that we'd be running something like benzoic acid. So we can come over here, we can, mistyped that, sorry, benzoic acid, and we can pick our level of theory, say PM6, and, calculate some of the results here. So we can see the trajectory that it goes to optimize its structure. So you can see it basically linearizes the molecule. Once we get a sense for that, we can turn off that component, see that molecule we have. We can download the input and output components to these calculations so that we have, in a sense, the raw data that was acquired from these computation. And that data from the computational output is also summarized here, some of the thermodynamic data. So we can grab this data, for example, copy it and put it into something like Excel or Google Sheet, a spreadsheet. So an example of that is shown here, the computational. I have a result, and this is showing, for example, benzoic acid. So I grab the molecule so that I have that for my report, and this is showing that you can just paste those results from molecalc here directly into a report here, listed as numbers, and then as I get all the various calculations done, I can summarize that. I can then use those computed results to calculate the heat of combustion of the material that I can then compare to experimental. And you can see I'm starting to generate the tables and figures I would potentially add into my report. Okay, so it gets us past the second component, then doing these simulated bomb calorimeter experiments, going to this simulator that we developed, which is here. There's a discussion and instructions associated with that. After reading some of the background material, you'll see we usually start with benzoic acid, and we can take that to the scale. We can decide on what would be an appropriate weight from looking at the background material. It's usually between 1 and 2 grams. You usually want the starting weight of temperature of the water to be a little lower than room temperature. The wire is fixed. Now, once we've decided that, it would be put into a bomb calorimeter. It would add a wire so we could ignite the sample. We would charge it with oxygen, and then this is the simulation to ignite the sample. And unlike collecting the data over time, the simulation basically simulates it all at once. And this is representative of the type of time versus temperature data you would get for doing a laboratory bomb calorimeter experiment. You can view the results. These are the type of results, very indicative of what you would get if you were in the lab recording this data from a thermocouple yourself. And now we can grab those results as well as all of the details about the experiment, and again summarize those, where I've summarized several of the simulated data here, as well as the conditions associated with it. So you can basically copy and paste that directly into a notebook that you can do kind of further analysis, like an example here where I've done a stack plot of several of the bomb calorimeter data all at once, where I'm comparing some standards to a fatty acid and glucose. So we can run this for several materials after it's calibrated. And this simulator also lets you do some of the basic data analysis, some of the extrapolation. It allows you to move this where you can try to kind of by eye see where these are equal area. For example, about, probably somewhere right about there, so we can get the initial and final temperature and get an idea of delta T. You can also go up here and download this plot so that you have a recording of this visualization of the data besides the raw data that simulate what you would get from the experiment directly. And again, there's a set of instructions here that talk about determining the calorimeter constant and then using that in the enthalpy of combustion type experiments. Okay, so that gets us, to where we would simulate benzoic acid as well as potentially a few other standards. Say, for example, a classic is different isomers of naphthalene to see how these isomers and their molecular structure change the heat of formation or the heat of combustion of the material. And then for our exact experiment in the fall 2023, we want to compare fatty acids to carbohydrates. So we can, when we're looking at samples, we can see what various fatty acids we have available, what various sugars or carbohydrates we have available, and make a plan of which of these we want to run, make sure we run computational analysis on the same materials. And then if we've done as we've gone, maybe as you do the computational and experimental components, you can pull up the start of your draft of your lab report, the template, and maybe start writing in the materials and methods. While it's fresh, while you've just done these experiments, is a good time to start writing a paragraph or two about what it would take to reproduce the experimental and computational components and all the details and any figures or tables you want to add to that. So that now we'll move on and look at, we have some of this data. If we've kind of followed this workflow, we'll already have some of the data in kind of a spreadsheet program or in something like Colab or a scientific plotting package. So we can continue to do some of the advanced data analysis and calculations and error analysis associated with this. And again, along every step, you can start adding these figures and tables into your report so that by the time you get down here, you really can now focus on just making sure your report is storyboarded. You can go from figures to tables, and just looking at those really get a sense for what this report is about, and that it kind of tells a story through the visualizations, the figures and tables. And now start finalizing your introductory material, your citations used, but your materials and methods that hopefully you wrote a first draft of, right after doing each of the computational and experimental components. And now you can work on kind of finalizing your report, your discussion, your results and discussion sections, etc., and finalize that off. So as a last thing, like for example, when we're doing our background material, we notice we might want to do, fats and fatty acids, and so we might want to show a diagram of kind of a fatty acid and a carbohydrate. So we can come up here and replace, so we can get an image here where I've made an image of a I grabbed off Wikipedia some kind of two-dimensional structures of glucose in a fatty acid system, and then I could start working on the figure caption and adding figures to my reports as I started making figures. For example, a bomb calorimeter, I could grab these figures and start getting them into my report, etc. So that I'm really working on this at every step along the way. From Scopus, I can directly start adding some of the citations and referencing those with either a reference manager or just directly in Microsoft Word or Google Docs, etc. So hopefully this gives you an overview of getting through Project 2 step by step, and kind of a workflow that I think works well for getting students to not save the project report to the very end and kind of work on it in steps as we systematically get through this project. Thanks.